It makes up most of the stuff in our universe, but we can't see it or weigh it, but we know it has to be there. This elusive substance is dark matter, and according to a new paper in the journal Nature Physics this week, it's all around us in our own galaxy, the Milky Way. To find out more about dark matter and what this new map of the dark matter in our galaxy might tell us, I went to speak to UCL astrophysicist Chamkor Garg, who's working on ways to detect dark matter here on Earth.
Dark matter is the material in the universe that actually holds galaxies and the structures that we're used to together. It's actually the dominant material in the universe. We used to think that most of the universe was made up of things that we're used to, protons, electrons and baryonic material, all this wonderful stuff. But it turns out that that's only about 4% of the universe. And the vast majority of the matter in the universe, sort of about 27%, is dark matter. It's matter, but it's not matter as we know it.
It's stuff that we know should be there, but we can't see it and we can't measure it and we can't weigh it.
We know that this matter is out there because we can infer its presence from what it's doing to regular matter that we can see. So the sort of the galaxies and stars and things, we can see that their motion is implying that there's a lot more gravity there. There's a lot more, they're feeling the gravitational force from other material, but we just don't see that.
A bit like an invisible hand.
Exactly, like an invisible hand, actually. It's and this hand is sort of holding galaxies and all that kind of stuff together, in fact. Without them, these galaxies, even our own galaxy, would have just ripped itself apart long ago. The reason we can't see it is because it doesn't interact the way normal matter, if you like, does. So light doesn't bounce off it, which means that it can't sort of bounce off and hit our eyes so that we can see it, and our telescopes can't see it either. We know that it feels the gravitational force because that's how we're sort of inferring its presence, but that's about all we know.
The thing about dark matter is obviously we can't see it with what we've got at the moment, we can't detect it with the technology we have right now. And it is something that's basically been proposed to make the maths work, to basically make physics work. Are there any other explanations for how these things that we can see, these sort of pushes and pulls, is there any other kind of explanation for that?
Yeah, there is sort of modifications to gravity. If one's willing to sort of, look at modifying our understanding of gravity itself, then you can play some sort of games and get things to work out just about. But actually there's a lot more evidence, in particular coming from the cosmic microwave background and sort of cosmological measurements, but then also galaxy cluster collisions and then large-scale simulation structures. So kind of, if we simulate how the large-scale structures in our universe were formed and how they evolved, that requires dark matter. And then there are other things that we can look out at, sort of galaxies that are colliding with one another, and you see what they're doing, and that says that there must be dark matter there also. And then, as I said, the cosmic microwave background, this sort of early imprint of the universe that is close to its birth, that also tells us pretty unambiguously that there's dark matter out there. So the dark matter's there, so we don't really need to invoke theories where we're mucking about with what we know of gravity. It's more a case of trying to understand what the nature of the dark matter is.
This new paper about dark matter in our galaxy, what's this about?
So we can look at galaxies sort of outside of our own and measure, in particular, the velocity of stars on the very edges of those galaxies. And you can see that those stars at the edges they're just whizzing around far too fast if they were being held in just by the gravity of all the other stars in there. And that's telling us that there's this extra mass, there's this extra gravity coming from this dark matter that's all around that galaxy. And that's all well and good, sort of looking out at other galaxies, but it'd be quite nice to know what the distribution or how much dark matter there is in our own galaxy. And that's really important if we're going to try and detect it here on Earth. It'd be quite nice to know, just how much there is. Is there any in our galaxy, and just is there any, sort of around our local neighbourhood? And this paper's telling us that yes, there is. It's a really nice measurement where they're taking lots of different stars and gas and sort of mapping the rotational velocity of each of those objects and showing us that look, they're just going around way too fast for there not to be dark matter right here, right now.
So by looking at how stars and things like that in our own galaxy are moving, they can infer that, there must be this much push from the dark matter here, there must be this much dark matter here.
That's right. It's more of a pull, really. They're kind of saying that, this is all being held together to allow these stars and other gas clouds to be whizzing around at the speeds that they're moving around at. They must be being held on by a lot of sort of force, a lot of strength there, and that must be dark matter. And that's what they're showing us. They've got a really strong sort of statistical significance here, stating that there is dark matter here in our own galaxy, and out to these kind of distances, where we sit right now.
This paper's looked at the amount of dark matter they think is in our galaxy, the Milky Way. That's still pretty big. Is there dark matter on Earth? Could there be dark matter here in this office?
Yes, as the Earth is sort of going around the Sun, and as the Sun is moving around the centre of the galaxy, we'd be experiencing a sort of dark matter wind coming at us. And so this dark matter sort of whooshes through the Earth all the time. And for every sort of pint of volume, any pint glass you hold up, there's roughly one dark matter particle in there, we think. And it's moving through at about 220 kilometres a second. So it's whizzing through all the time. There's millions of these things going through your body, all the time. It's just a case of, do any of them interact? Do they scatter? Do they sort of bounce off regular atoms? If they do, great, because then we've got a chance to actually find them with terrestrial detectors that we put underground. If they don't, and we don't see it that way, there are other ways that we could go about it. As I say, we can try and make it in accelerators, such as at CERN, where you sort of smash particles together and try and create dark matter anew, just as it was created, early on in the Big Bang. The stuff that's out here right now, we could try and make our own and sort of prove that we understand what this stuff is. Or dark matter particles, when they come together and collide with one another, if and when that happens, in sort of dense regions of space, they annihilate into other particles, standard model particles that, okay, we're not very good at finding dark matter yet, but we are quite good at finding things like positrons and gamma rays and electrons. And when these dark matter particles come together, they annihilate, and the debris that they kick out from this collision are things that we can detect. And so that's the indirect detection method. So there are ways to go about sort of finding this stuff. What we're hoping for is, of course, for all of these things to come together, and we get a really good handle on what this stuff is through all these different detection methods.
Now we know roughly, I guess, how much dark matter we think is in our galaxy. What next? What's the significance of this finding?
We had a good idea about roughly how much dark matter there is in our galaxy and in our local neighbourhood. But what this paper's allowed us to do is really, increase our sort of statistics in mapping how much dark matter, on average, there is in our own Milky Way, and extending out to where we are right now. And it's giving us a good handle, some nice evidence, some confidence for when we do go and search for dark matter. It's really telling us that, look, it's okay, there is stuff here. We would expect to see this stuff if it interacts the way we think it does. And if we can start to do this, with more and more precision, with greater accuracy, we might start to figure out the distribution of dark matter also. So, is it clumpy? Is there more of it over here than over there? Rather than just sort of average measures for the galaxy as a whole, we can start to profile it. How much is there in the centre, in sort of where we are, and then out further? And then also the distribution of it. That's quite important. We might be sitting in a pocket where there's a lot of dark matter, or there's not much dark matter. And that really impacts our chances for finding the stuff, at least directly, not so much indirectly, or with accelerators.
So you're looking for dark matter here in UCL, in the centre of London. Do you want to show me how you're doing this?
Well, we're working on a project that will actually be housed in South Dakota, in a gold mine, 1.5 kilometres underground. But to prepare for that experiment, sort of some R&D and actually getting bits and bobs together for it, that's what we're doing here in our laboratory at the moment. But the detector itself has to be deep underground. Although we've got many dark matter particles sort of whizzing through us all the time, we've also got lots of other things up on the surface of the Earth, like cosmic rays and other radiation. So these detectors have to go down deep underground, where they're shielded from any of that sort of radiation.
And the Victoria line.
Exactly, yeah. Far from any of that kind of stuff. Nice, stable, radio quiet environments.
So let's go and have a look.
Okay.
Okay. So this, basically, it's about the size of a washing machine. It's a box that's wrapped in tinfoil. What is this that we're looking at?
That's right. So what we're putting together here is just a small setup where we can liquefy noble gases. In this one, we've got liquid argon. And the reason we're doing this is because this is the target material that we use when we're looking for dark matter. So noble gases, when you liquefy them like this, you can pack a lot into compact volumes, and whenever any particle sort of comes in and hits an argon or a xenon atom, it produces a huge amount of light, and that's useful because we can then detect the light and say that, okay, something just happened there, something just hit one of the atoms. So the dark matter detector that I work on is going to be filled with liquid xenon and housed down in South Dakota, sort of 1.5 kilometers underground. And so this sort of noble gas research and looking at, you know, the different technologies that you can use to actually pick up that light is what this stuff is all about, really.
So let's have a look at this. We've got this enormous square thing, like it is about the size of a washing machine. It's wrapped in foil. Coming out of the middle of the top of it are some sort of discs and rivets and tubes connected to a wall of steel covered in more tubes and dials and taps. What's coming in and out, and what's this thing making the noise down here?
So it's actually a lot more simple than it looks, at least in principle. So what we're trying to do is just take some gas. Behind there we've got some argon bottles, and it's argon gas, and we want to condense it into a liquid inside this central pot. And the way we're going to do that is by filling this outside, this pot on the outside, also with liquid argon, so that, you know, this outside is all filled with argon, and inside the gas will then condense because it will also be at that temperature and turn into liquid as well. But the stuff on the inside is going to be very clean and very pure. And so the rest of this stuff, you know, on this wall of pipework, it's just the infrastructure to keep that gas clean and keep it purified, so that when it actually goes into this bucket, this chamber, we'll be able to do some physics with it. We'll be able to, you know, put a source next to it, for example, and see light and charge liberated from where the interactions are occurring. And then we can test our detectors and things for how well it picks up this charge. And then that thing down there is just a vacuum pump, actually. It's just evacuating the whole chamber so that it's ready for us to pour our gases in.
And how do you actually detect the particles from this? So I can see that there's a little window in the top of one of these tubes. How are you actually detecting whether particles have interacted with your gas in here?
It's the first detector that we're going to be putting in this is called a photomultiplier tube, and typically the large dark matter detectors, sort of the real dark matter detectors, are using these as well. And what essentially they're light bulbs in reverse. So with a light bulb you'd have some electric current in and some light comes out. With these things, light goes in and we get an electric signal coming out of it. So the dark matter particle comes in, it hits your xenon atom. In doing so, the xenon atom gets excited, and when it de-excites, it sort of sheds some light. That light then goes off, and we detect it with one of these photomultiplier tubes, these sort of light bulbs in reverse. And that's what gives us an electrical signal, and then we can say, okay, something just happened there.
But how do you know it was dark matter and not some other kind of rogue stray particle?
Good question. That's where all the analysis comes in. So you have teams and teams of people sort of poring over this data, and xenon and some of these gases are really quite useful in that they give different signatures depending on what hit them. So if a gamma ray comes in, for example, and hits an electron whizzing around a nucleus, it will give us a particular signature of light. Whereas if it comes in and hits the nucleus of the atom, it gives a different signature. So we can tell, you know, we can tell these two apart. There's subtle differences, but we can start to tell them apart. And then we shield the detector from all the stray particles. So going deep underground is to shield against radiation from space, but then the detector itself is housed within sort of 5 meters of water, and then within that there's an outer detector, and then within that there's another one. So it's sort of an onion shell configuration where only the very central inner core is where we're looking for dark matter, and no other radiation can really penetrate in there.
So this device here, it's a few feet across each way. How big will the detector be when you build it in South Dakota?
So the one that we operate there at the moment is called Lux, and it's about the size of an adult human. So it's not so large, but it still packs into it 350 kilograms of liquid xenon. So it's a dense medium, and which is good. It makes the detectors quite manageable. The next one that we're working on is Lux Zeppelin, and that's sort of bringing together the Lux experiment, which is based in the States, and the Zeppelin program that the UK led up at Balby Mine. And this detector is going to be a lot larger. It's actually, geometrically, it's not so much bigger. It's still the size of a human, but a larger human, if you like.
I'm a very small human, so a bigger human.
It's sort of a couple of meters high and a couple of meters wide, and it's going to contain within it the sort of active target. The bit we're looking for xenon will be about looking for dark matter will be about 7 tons. And it will contain within it about sort of 9-10 tons of liquid xenon, as opposed to the few hundreds of kilograms that Lux has. And that's a sort of scale of detector that we've been trying to get to for a long time. We've known that we want to have, sort of a ton to 10 tons of liquid xenon to really have the sensitivity where we think we'd start to see dark matter and really look at, start ruling out different theories and things, and or detecting the stuff.
How long are you going to look for? Because obviously if you're looking for particles that we don't really know they're there, we don't know how much there might be in the immediate environment of the Earth, how long are you going to run this experiment for?
Well, so Lux Zeppelin we will build over the course of a few years, and then it will take data at least for about 3-4 years. And that's enough for us to sort of, get... allow the detector to do its job, really, hit its top speed, if you like. Once we have that data, then we can actually sort of pore through it and have a look and see if we've seen any dark matter there. The reason we've been going for, this size of detector is because although we've been searching for many, many years, decades, in fact, we've known... there have been models, there have been a lot of theories that tell us that, dark matter could be this stuff. It could be weakly interacting massive particles. And there are other theories, sort of extensions to the standard model of particle physics, that tell us that, look, dark matter particles sort of naturally flow out of this theory also. And we would expect those to be sort of here, in terms of a phase space, in terms of this is how likely they are to interact, and this is how massive they're going to be. That then tells us what sort of size and sensitivity of detector we need. And with Lux Zeppelin, we reach that. We get down to sort of, the bottom of those models and those theories. So with this one, we're confident that if these models are correct, we should start to see something. And if the models aren't correct, we'll do a good job at sort of ruling those out and saying, that's not, okay, dark matter isn't there, we need to go back and think of other things here. But how long will we keep searching? Given that we know it's there, I suppose, we keep searching till we find it. Right? It's too big a problem just to give up on. Right? This is 85% of the mass of the universe. Right? And just to say that it's a tough job and we can't, it hasn't just appeared with our first efforts. Well, it doesn't matter. We've got to be smarter and look for other ways of going about it.
Chamkor Garg and his dark matter detector. And in case you were wondering, the tin foil is wrapped round it to help keep it cool.